I am a structural geologist, and as a structural geologist I'm interested in structures that form secondary, so-called tectonic structures. Structures that form by folding and faulting of, say, sedimentary layers. And there is a whole range of structures. You can go out in the field and you can map them, you can measure up the orientations, geometries, go back and plot the data in stereo nets and things like that. And that's a lot of fun, it's important, but it doesn't stop there. The most important part is to use the structural information to try and understand what's going on a larger scale. And that's why structural geology is very closely linked with tectonics, including plate tectonics, where the motions in the crust, in the lithosphere, the motion of plates is what creates structures. So we can use structures if we know what we're looking at, if we understand how the structure is formed. We can use that information and try and say something about, for example, plate motions in the past. As an example, we can take faults, and there's different types of faults. For example, there are extensional faults, that's normal faults that are involved during the extension and stretching of the crust. And there are reverse faults and thrust faults that form when the crust is being shortened. Now, right now we are just outside of Las Vegas in the Red Rock Canyon area. We're looking at some red and yellow sandstones in the background. Now that's Jurassic sandstone, the Jurassic Aztec Formation. And on top of those sandstones, back there and high in the mountain there's another type of rock, another rock unit that is older, that is Cambrian and Devonian. And those rocks, those old rocks, are resting on top of the relatively younger rocks, the Jurassic rocks. So Cambrian rocks on Jurassic rocks. And between those units there is what's called thrust fault. So that thrust fault formed when the part of the crust during shortening was ripped off and put on top of another part of the crust. So you get older rocks on top of younger rocks. So that's one of the characteristics of thrust faults. Just understanding that relationship enables you to say something about the size and the magnitude of the shortening of this part of the United States sometimes after the Jurassic, probably in the Cretaceous. And this is actually the Sevier orogeny, and that particular thrust that separates the upper plate, the Cambrian from the Jurassic, is called the keystone thrust in this area. Let's have a look at the plaster experiment where we produce reverse faults and thrust faults, a little bit like what we have here in Red Rock Canyon outside Las Vegas. This is an experiment where we are shortening wet plaster in a box, shortening by pushing one side toward the other. And the nice thing about experiments is that we can see not only the end result, but we can see the entire development from the beginning to the end. And in this case, we can see which of the reverse faults developed first and which developed last, and how they deform and change orientation during the shortening. So in this case, we have sort of a normal in-sequence thrusting history, and the result is a very nice imbricate structure. So that's about shortening and the structures that form during shortening of the crust. We could also extend the crust, and like I said, we get normal faults, extensional faults. And we have to go somewhere else to, well, there are extensional faults here too, but let's go to a place in Utah to show you what an extensional fault looks like. The geology of southern Utah is beautifully exposed, And right here we're flying over Arches National Park, and we can see sandstones of Jurassic age with several sets of fractures. If we go down on the ground, we will see not only fractures but also faults. Hey, look at those beautiful structures on the other side of the road. Those are faults affecting sedimentary layers, sandstones, shales that were once continuous layers, and now they have been affected by these faults in a very interesting way. In this case we have normal faults. Normal faults are extensional structures. That means that at some point in time forces were trying to pull these rock layers apart, and they partly succeeded and these faults formed. So that's useful information for us as geologists, what happened back in time. This place in Canyonlands is a really interesting place where we can see that the displacement on one fault is decreasing. At the same time, another fault picks up the displacement. So the displacement is basically relayed from one fault to another, and we have a relay zone. And in between these two faults, there's what's called a relay ramp, where layers have been folded. And in this particular case, we actually have two sets of relay structures. And we have actually what's called a graben step-over structure, where one graben dies out and another one continues. Both being parallel with an offset. In some cases we have stretching in two directions, like in these turbidites in Portugal, where we have quartz veins, a vertical set of quartz veins and a horizontal set of quartz veins, and together these imply vertical and horizontal stretching. So we have a structure that is called chocolate boudinage structure, and the strain field that it implies is flattening strain. So we've seen sandstones and sediments being deformed, forming faults and fractures. In this case, the sediment has not fractured. It has deformed in a very different way. These pebbles and cobbles that were once part of a conglomerate has now been stretched out into these very elongated objects, almost cigar or walking stick-shaped geometries. And so the rock in this case behaved like a very soft material, and we're talking ductile or plastic deformation. And this happens deeper down in the crust, where the temperature gets high and rocks start to flow. So a very different expression of deformation. Temperature, crustal depth are very important parameters when it comes to the way that rocks respond to forces and stresses in the crust. So here's another example of rocks that have deformed in the ductile fashion. We're looking at gneisses, and we're looking at the fairly nice fold. So to fold a gneiss like this, we need temperatures of, say, 350 degrees or more. So we know that we've been down at least 12-15 kilometers in the crust. So we're in the ductile regime. The aim is to understand the history behind the formation of these structures, the processes involved, and to understand what was going on in the past at the time when the structures formed. Many possibilities. We talk about tectonics, so structural geology and tectonics are sort of walking hand in hand pretty much all the time. We use structure to understand the tectonic history. So tectonics is more about large-scale motions, oftentimes plate motions. And when plates move, they create structures. So if we know the plate motions, we would expect certain types of structures to form depending on how the plates move. I mean, if plates converge, you would expect to find what's called reverse faults, thrusts, folds, large-scale folds, and mountain chains, orogenic belts. Whereas when plates move apart, and especially when continents internally start to break up and move apart, one part moving one way, the other part moving the other way, we expect in the upper crust at least normal faults, what's called extensional faults, and those kind of things, extensional shear zones. So we could anticipate certain types of structures depending on the plate motion picture, the kinematic picture. We could also go the other way around, which is what we oftentimes do as structural geologists. We go in the field, we map out the structures, and then we say something about the large-scale picture. And that's exciting. It usually takes a lot of data collecting, a lot of field work, for example, and maybe you need to do some modeling, numerical modeling, maybe some physical modeling, to actually understand what is going on structure-wise. So there are a whole range of different types of structures. Some form high up in the crust, some form deeper down, but they also depend on the kinematic picture and the stress picture.